A primary purpose of modern operating systems is to allow for multiple processes to run concurrently, meaning at the same time. The problem, of course, is that each CPU core can only execute the code of one process at a time, and the OS's own code can't run on a core at the same time as any process. The solution then is to have each CPU core alternate between running each open process and alternate running processes with running OS code. So here, if we have two CPU cores and three open processes, A, B, and C, notice that each process only runs on one core at a time. At no point does, say, process B run simultaneously on both of the two cores. Also notice that OS code always runs on each core in between each process. What's happening here is that a portion of the OS, called the scheduler, runs after each process to decide what OS work, if any, should be done and which process should run next. The question then is, how does the currently running process get interrupted? Left on its own, a running process would continue indefinitely. When any hardware interrupt is triggered, however, the interrupt handler passes off control to the scheduler rather than handing the processor core back to the interrupted process. The scheduler then decides what OS code to run, if any, and what process should run next. Laid out in full, the scheme called Preemptive Multitasking works like this. Just as a side note, the problem here is that we haven't learned about hardware interrupts yet, so you might not know what they are, which will make it hard for you to understand the following steps. But if you already know what they are, you can stay. If not, however, I advise you to come back here to this course once you take the course about interrupts. So where were we? The preemptive multitasking works like this. First, the CPU receives some hardware interrupt, then the interrupt stores the program counter so that the interrupted code can resume later. The interrupt invokes the appropriate handler. The handler itself saves the state of the other CPU registers so that the interrupted process can be resumed later. The handler does whatever business the interrupting device needs. The handler then invokes a scheduler, and the scheduler selects a process to run. The scheduler then restores the CPU registers to the state they were in when that process was last running so that that process may continue. And finally, the scheduler jumps execution to that process. You may now be wondering two things. First, what if no interrupt is triggered by any device for a long time? That would allow the currently running process to hog the CPU when generally we want each process to at least get a little time on a regular basis, say every several seconds or so. A video game, for example, typically can't go without CPU time for more than a fraction of a second, so it would be no good if some other process ran without interruption for a second or more. To ensure that the scheduler gets to run on a regular basis, whether any I/O devices need attention or not, a clock device on the mainboard is configured to send an interrupt on a regular basis, say once every 10 or 20 milliseconds. Thus, the system guarantees that the scheduler gets the opportunity to change the running process on each core at least several times a second. The next thing you might wonder is how the scheduler chooses which process to run next. Using the simplest algorithm, the round-robin algorithm, the scheduler simply runs each process in turn one after the other. While this ensures that every process gets run on a regular basis, the more sophisticated algorithms used by Windows, Linux, and other modern operating systems attempt to take into account which processes need processor time more than others.